All right, part 2, how mining works. Let's have a look. So we left off last time over here where we have this block, and we now know that we can control, or we can vary the hash of the block by varying the nonce, the number, the extra field that we identified. Okay, so how does this tie in with mining? Well, let's have a look. The first thing that we're going to need to do is to make a statement. And the statement is that a hash is a number. And if you already know this, then bear with me. This will just take like a minute. If you don't, then this will be very useful for us going forward. So here is an example of a hash. This is a proper SHA-256 hash. It takes up 64 bits, 64 digits. There's 64 digits here, 256 bits. And the statement is that this is actually a number. It's not just a word. It's not just a combination of characters. It's not just a label. It's an actual number. So you can increment it. You can do mathematical operations with it. And why is that? Well, a hash is actually a hexadecimal number. So here you can see digits, so from 0 to 9, and also you can see some letters, but the letters are limited to F, so it's A, B, C, D, E, F. And what a hexadecimal number is it's like a decimal number, but instead of just having digits from 0 to 9, it also has those 6 extra ones. So A stands for 10, B stands for 11, C stands for 12, D stands for 13, E stands for 14, F stands for 15. And so that's all there is to it. And we can actually convert this hexadecimal number into a normal decimal number, and it'll look like this. So there's our decimal representation of our hexadecimal number. As you can see, the number is visually longer, and that's because in the decimal system we only have 9 digits, whereas in the hexadecimal system we have, in the decimal system we have 10 digits. Funny. But in the hexadecimal system we have 16 digits. So therefore, every digit can encode a higher value, if you want to call it that. Every digit will encode a higher value in the hexadecimal system, and therefore visually the number is shorter. But in essence, the overall value of the number is actually exactly the same. It's just represented in a different system. It's like we can take a decimal number and convert it to a binary, into ones and zeros. It'll be very long, but it'll still be the same number, just represented in a different system. Same thing with hexadecimal. We can take the same decimal number, convert it into hexadecimal. We can convert it to any system we like. We can convert it into a system of the base of 57 if we wish. But just that those are the commonly used ones. The decimal one, which we use in the real world, binary, which computers use, hexadecimal is also used for some things. One of them is hash numbers. Then here's another example. There's another hash number, also, of course, hexadecimal. This is another SHA-256 hash. As you can see at the start, there's leading zeros. You don't have to write them out, but I included them here just to illustrate that the visual length of this number is the same as the previous one. It is also 64 characters or digits in length. And if we convert this to a decimal number, there we go. There's the decimal version as well. Don't have to write out the leading zeros, it's just a smaller number. And here's another hash. It's also, this one's even smaller because it has so many more leading zeros, and this is its representation in decimal. Okay, so we've identified that hash is a number. What does that give us now? Why is that valuable? Well, now we can actually illustrate this. We can draw hashes because we know that they're numbers, so we know they're consecutive orders. Some are smaller, some are bigger. So let's draw a pool of hashes. We'll call this pool the pool of all possible hashes. At the bottom we have the smallest ones, at the top we have the largest ones. And basically what this is all possible variations of this hash value. So starting from the smallest at 0000, and then going all the way up like that. It doesn't matter like how exactly we structure it, but like, well, let's say it goes like a snake all the way up. It increases until it gets to the very top, where what will the highest one be? Well, that's when all of these digits are F all the way. So that's the highest. And so we're just going to order them like that, and this is going to be like a map for us. And so now we're going to see where these hashes fall on the map. So we know that, well, let's say this top one falls somewhere over there. This one is smaller, so it has to fall lower. This one smaller falls lower. And so there we go. Those are our hashes. They're illustrated on the map. We can get rid of the decimal representations now. And this leads us up. This is a very nice setup. This is in combination of the previous tutorial. Very nice setup for what is mining all about. Like, why is, what's this whole fuss about mining? How does it work? And start with how does it work, then we'll get to the fuss after that. So how mining works is, in essence, the blockchain system or the blockchain algorithm will set a target. So there's a target that's set for miners to accomplish a certain hash. So let's say the target's over here. Target There we go. That's our target. And the way it works is any hash higher than the target doesn't count. So if you find a hash for your block that is above the target, that doesn't count. That's not good enough for the blockchain. It has to, in order to be included in the blockchain, it has to be below the target. And the important thing to know is this is completely arbitrary. There is no economical reason for it. There is no like logical or computational, mathematical, cryptographical reason for it. It's just a way to put hurdles in the way of miners, to create a challenge for them to solve. That's the only reason there is this target. No other reason. And so in this case, if a miner found this hash, it wouldn't count. It would be not good enough. They would not be allowed to create a block with this hash number. This hash is also not good enough. It's above the target. But if you found this hash, you'd be welcome to create the block. You'll be allowed to create a block, and that's when you would be considered the miner who actually mined the block because you found a hash like that. And this is like just at a high level. We will go into the detail like in a second in this. But before we do, I wanted to give you guys a small tip that a good way of thinking about the target is actually in terms of leading zeros. So as you can see, the lower you are, the smaller the number, and the more leading zeros there'll be. So if you think of the target rather than as trying to remember what the target is in terms of hashing, just remember the number of leading zeros. For instance, 4 leading zeros. So let's talk about that. And actually in the practical tutorials, Adlan will be showing you how to code a blockchain, and you will be using these 4 leading zeros. You'll see that in the practical side of things. So that's how we're going to think about the target. And now let's discuss what we just talked about, the whole mining concept. I know it's right now it's very vague, very unclear. So let's make it clear. Let's make it super clear. So after this tutorial, you walk away and you're 100% sure what mining is all about. So let's go back to what we discussed in the previous tutorial. So here we've got the block, and we know that what we have inside this block is the block number, the nonce, the data, the previous hash. And most of the fields here you cannot touch them. You cannot tamper with them. You cannot change the block number because it's a block number. So we're trying to add, forget about this part. It's just, we only have the chain on the left. There's no more chain on the right? So this doesn't exist. So we want to add a new block. So we know that block number, we're going to be adding block number 3. Okay, so you can't change that. The data in the block. So as we discussed, we don't want to change the data. We cannot change the data. In reality, there's a bit more to it. Like in module 2 of this course, we'll understand how we can change or vary the transactions that go into the block. But for now, for us to understand how mining works, it's good enough to agree that we have this set of transactions that needs to go into the block, and we cannot change it because if we agree that the list of transactions is set, then we cannot change any details of each transaction because we don't want to tamper with the data. And that's the whole concept, whole point of blockchains, that it's an immutable ledger. Then we cannot also change the hash of the previous block. We cannot change this value because it has to be cryptographically linked to the hash of the previous block. So the only thing that we can actually change in this whole block is the nonce. And the nonce allows us to vary the hash of the current block. So let's see what that means for mining. So if we plot this hash onto our map of hashes, you'll see that it might be somewhere over there. Let's hypothesize that it's over there. And that's the hash, and this label is just to remind us that this hash was generated from this block when the nonce was 23. So next, let's change the nonce, 22. Now you can see the hash is over here. It's a smaller hash, and that was generated by nonce 22. And so we can just keep going doing that because we will not be allowed to add this block into the blockchain until the hash is below the target. So all we can do is just keep guessing different nonces. As you can see, there we go. And that's essentially what miners do. Miners just sit there and they change this field, they change the nonce in order to try guess a value of the nonce that will generate a hash below the target. That's as simple as that. And once they do generate such values, so for instance, they find a nonce at some point at random by accident through brute forcing, they find the nonce, for instance, 5012, that generates a hash below the value, then they win. That's it. They get this nonce is commonly called among miners, it's called the golden nonce. And because it generated a hash below the target, as you can see, has those 4 leading zeros is below the target. And that's it. So then once that's done, they're allowed to add the block to the blockchain and they get their reward, which again, we'll discuss in module number 2. But the whole point is that at that point, that's when the block is accepted by the blockchain, only when the hash is below the target. The rest of the time, all these, the whole thing that these miners are doing is they're just sitting there, or, well, they're not sitting, these are nodes, these are rigs of nodes, and they're just churning away, they're just iterating this nonce, changing it to hopefully guess the right hash, and whoever guesses it first adds a block, and then the whole thing starts again for the next block. So there's a couple of important things to point out here. So we already discussed about the transactions, and we'll talk more about that in module 2. The important thing about hashes is the avalanche effect. So remember we discussed the avalanche effect, that by changing the nonce a tiny little bit, the hash changes completely. And why that's important for mining is to keep people from cheating the system. So here you can see that the nonce for 23, so the hash for 23, let's go back. So here you can see that the hash for 23 was up here, then the hash for 22 is down here. And if, for instance, if changing the nonce a little bit would change the hash a little bit, that would allow miners to predict that, oh, okay, looks like by reducing the nonce, the hash is going down. So all I have to go is 21, 20, 19, 18, 17, and finally I'll get below the target. I'll get over here. But that's not the case. As you can see, at 21, it goes up here. At 76,000 is here, but 143 is here. It's completely all over the place. It's completely unpredictable, and that's a very important feature. Now we can see that why that's such an important feature of the hash, why the avalanche effect is so important in the hash, because without that, this whole cryptographic puzzle, this concept of finding the hash is called, the right hash is called a cryptographic puzzle. This whole cryptographic puzzle would not even exist, because you could just like find your way, like a shortcut into getting the smallest nonce. And that even further illustrates the importance of the hashing algorithm. Like the reason for us using the hashing algorithm is because you cannot reverse engineer it. You cannot crack it and predict what hash you will get based on the nonce you input. As soon as somebody is able to do that, the whole of this concept is going to fall apart, because people will be just being able to predict the nonce and then just put in, and they'll know what hash they get, so they won't have to put in the work in order, put in like hours and hours and hours of machine time in order to crack this nonce, in order to get the right hash below the target. They'll just put in the nonce, they'll calculate what nonce they need to get a hash below the target, and that's it. They will put in the block. So that's what the SHA-256 promise is, that nobody's been able to crack it. There's been attempts, lots and lots of attempts to do that. But people haven't gotten even close to cracking it. There were previous hash algorithms, such as SHA-1, MD, I think they're called MD4, MD5, which have been cracked, but every time they've been updated into a stronger one. So now we've got SHA-256, there's also SHA-512, there's SHA-3, and so on, that algorithms that are even stronger. But for now, blockchains use SHA-256. So some important features to remember about, or to know about the hashing algorithm, why it's so important in blockchains. Okay, so that's a second important thing that we needed to point out here. So there we go, that's our golden nonce at the bottom. And yeah, so that's in essence how mining works. You just need to keep iterating the nonce until you get a hash below the target. Then you get to add that block, or whoever gets there first gets to add that block, and then the whole thing starts again for the next block. Yeah, and so finally, I just wanted to ask you if you see there's an error on this slide, and I was wondering if you were able to pick it up, if you were able to see it. Actually, I just noticed it myself just not so long ago. This previous hash couldn't be possibly correct, because it has to start with 4 leading zeros, right? Why the block number 2 would have not been accepted into the chain if this hash started not with 4 leading zeros. So that's an error on my side, on my part, preparing these slides, but it illustrates, kind of like reinforces the concept that blocks would have to be below the target. The hashes have to be below the target for blocks to be accepted. So in the proper blockchain, this previous hash would have been also below the target. So there we go. That's in a essence, like this is how conceptually mining works. Of course, there's lots more to it. Like, for instance, we talked about the fact that we can actually there's ways for us to control what transaction going into here. We'll talk about that in module 2. There's more to the nonce. There's more components to the nonce. There's actually more fields that go into a mining block, and we'll talk about those things in module 2. But so if you already have some questions and some things that you might have read somewhere about blockchain mining, or you have some ideas already, and some things for you right now are you've got more questions that haven't been answered yet, don't worry, we'll answer those in module 2 of the course and going further in the further tutorials. But right now, this is what we need. This is the foundation that we need in order to progress with this part of the course, module 1, and with the practical tutorials that are coming. And after that, we'll build on top, and we'll increase our foundation and increase our knowledge incrementally as we go through the course. On that note, thank you so much. I hope that now it's clear how mining works and what this whole fuss is about, what the cryptographic challenge is, why people are racing to get to the best, to the golden nonce, and why there's so many miners around the world, why they need the computational power. And I can't wait to see you in the next tutorial. Until then, enjoy blockchains.